Special relativity. Deriving Lorentz transforms from light interference invariance. What we need to do is to make the interference pattern upon the rotation of the device invariant using the same calculation steps of Michelson and Morley. In other words, the only thing we need to do is to modify our transformation relative to the ether so that the light interference pattern remain invariant when the device rotates in the moving frame. What we know is the origin of each observer is moving at speed v relative to the other. Light is moving at speed c over x-axis and x'-axis relative to both observer. Each observer measures his own time. The light interference pattern remains invariant when the interference device is rotated relative to an observer moving at uniform speed from the interference device. Space-time transformation are linear. The origin O' is moving with speed v relative to origin O, and the coordinate of origin O' relative to O is 0. Substituting that in space-time relations. Dividing the first equation into the second equation. The origin O is moving with speed negative v relative to origin O', and the coordinate of origin O relative to O' is 0. Substituting that in space-time relations. Hence, from the first relation, now we have the following equations. Substitute that in space-time relations, we obtain. We assume that a ray of light propagates at speed c along x-axis and x'-axis for both observers. The speed of light is the same in x-axis and x'-axis direction, which is the direction of frame movement. Substituting that in the space-time transformations. Solving for t in the second equation. Substituting that in the first equation. Solving for the coefficient g. Now we have the equations for coefficient E, F, G, H. The third formula originates from the invariance of light interference for both observers when the device is rotated. Finding delta Ti at 0 degrees. At time t1, the light is emitted at point A1. The relation between space and time at that point is the following. At time t2, the light reaches point A2. The relation between space and time at that point is the difference in space along x-axis is the difference in time. Relative to k, the light has traveled a distance c times t2 minus t1 from point A1 to A2. From the geometry of triangle A1, A2, M2. Since the mirror at the origin of the coordinate frame k' moving at speed v relative to k. Subtracting the first equation form the second. The A in terms of k'. Here we assume y2 minus y1 equals y2' minus y1'. Substituting y2 minus y1 equals a and x2 minus x1 equals v times t2 minus t1 in the right angle formula, from which we obtain the period of time the light takes to travel from point A1 to point A2. At time t3, the light reaches point A3. The relation between space and time at that point is The difference in space along x-axis between point A3 and point A2 is relative to observer K. The light has traveled a distance c times t3 minus t2. From the geometry of triangle A2, A3, M2. Since the mirror at the origin of the coordinate frame K', moving at speed v relative to K. The difference in space along x-axis is. Here again, we assume y2 minus y1 equals y2 prime minus y1 prime equals a. Substituting that in the equation c times t3 minus t2 square, we obtain. From which we obtain the period of time the light takes to travel from point A2 to point A3. The total period of time the light takes to travel the path A1, A2, A3 is. From which we obtain the time the light takes to travel from mirror 1, 2 and 3 when the device is rotated by 0 degree. Finding delta T2 at 0 degrees. At time t1, the light is emitted at point B1. The relation between space and time at that point is. At time t1, the light is emitted at point B1. The relation between space and time at that point is. At time t2, the light is reflected at point B2. The relation between space and time at that point is. Notice that the T1 equals T1 capital and that A1 equals B1, but that is not the case for time T2 and point B2. The difference in spacetime along x-axis between point B2 and point B1 is the difference in time. But the term x2' minus x1' in frame K' is the arm length b of the device, hence we substitute that in the previous x-coordinate difference and time difference. Relative to K, the light has traveled a distance c times t2 minus t1. This distance is equal to x2 minus x1. Substituting that in the coordinate difference relation. Solving for t2' minus t1' in the first relation. Substituting that in the second equation. Solving for t2 minus t1. Rearranging. Rearranging. At time t3, the light reaches point B3. The relation between space and time at that point is. The difference in space along x-axis between point B3 and point B2 is. But the term x3' minus x2' in frame K' is the arm length in negative sign b of the device. Hence, relative to K, the light has traveled a distance c times t3 minus t2. This distance is equal to negative x3 minus x2, since x3 minus x2 is negative in sign and c times t3 minus t2 is positive in sign, hence. Substituting that in x-coordinate difference. Solving the first relation for t3' minus t2'. Substituting in the second equation. Solving for t3 minus t2. Rearranging. Now we have the total period of time the light takes to travel the path B1, B2, B3 is. Substituting. Rearranging. Finally, difference in light rays arrival time at mirror M2 when the device is at 0 degrees. Now we have delta Ti at 0 degrees and delta 2 at 0 degrees. The difference in ray arrival time between ray 1 and 2 is delta T0. Difference in light rays arrival time at mirror M2 when the device is rotated 90 degrees. We have found the time it takes ray 1 and 2 to reach mirror M2 when the device is rotated by 0 degree. Delta T1 at 0 degrees for the case. Perpendicular ray 1 and A is the perpendicular arm. Delta T2 at 0 degrees for the case. Parallel ray 2 and B is the parallel arm. When the device is turned by 90 degrees, the perpendicular arm becomes B and the parallel arm become A, as shown. Hence, the difference in time when the device is turned by 90 degrees is delta T1 at 90 degrees for parallel ray 1. Delta T2 at 90 degrees for perpendicular ray 2. Hence, the difference in light rays arrival time at mirror M2 when the device is rotated 90 degrees is delta T at 90 degrees. Difference in light rays arrival time at mirror M2 when the device is rotated from 0 degrees to 90 degrees. Now we have delta T at 0 degree and delta T at 90 degrees. For the interference pattern to remain invariant when the device is rotated from 0 degrees to 90 degrees, the difference of the differences of arrival time of ray 1 and 2 must be 0. Substituting. Rearranging. Rearranging. This difference must be 0. Dividing by the term 2 times a plus b and multiplying both sides by the term square root of 1 minus v square over c square. Rearranging. We have found before the equations for the coefficient h, e, and g. Finding the coefficients e, f, g, and h of spacetime transform. Substituting h, e, and g in the equation. We find rearranging. Dividing by f square. Rearranging. Solving for f. Rearranging. The rest of the coefficient can be found by direct substitution. Finding the formulas of spacetime transform. The spacetime transformation will be which are Lorentz transformations. Now we can make sure that the speed of light is invariant in all direction and that all light rays propagates a spherical wave by finding the invariance. X square plus y square plus z square minus c square times t square equals x prime square plus y prime square plus z prime square minus c square times t prime square.